let me ask you, Sean, well, the things you could be interested here are the use of SysML, the language itself, the creation of a model, or the mechanical engineering of putting a blood analyzer together. I'm not going to cover the chemistry. I took organic chemistry one year, and that was enough for me. No more organic chemistry.
Lots of memorization, Brian.
I went over to engineering as quickly as I could. Okay, so what do you guys, what would you like to see? Okay. So basically, I want to show you how to use SysML to build a real world product. How about yourself?
I think the SysML is.
Yeah.
Right. I'm also interested in the end-to-end how everything together.
Yes.
That's a real product.
Yes. And I got a surprise for you guys. At the end of the presentation, I'm going to show you the machine running. It's not everybody that gets to see. A lot of people start at the front end. They do all these designs and then they walk out the door and then they don't see anything at all. After that, it's a dead end, for them. And they're great at building product, except after they put a couple of diagrams together, they fall on their face. So how about yourself? What would you like?
The modeling.
The modeling language, okay. And you're?
Yeah, I'm not familiar with SysML.
All right, so what I'm going to do is I'm going to spend a little time on the modeling language, and every time I show you a diagram with SysML in it, I'll explain what that diagram is. Do you guys know UML?
But yeah.
Yeah, okay. UML? Okay. Do you know the oval in UML for process? Okay, very good. All right.
I've only heard of UML.
All right, okay. So we're going to start. If you stop the echo. I don't like the sound of my own voice, actually. Okay, so we're going to use SysML, and we're going to start from scratch. We're going to capture the requirements. And then we're going to, after we capture the requirements, we're going to do a client-side design, and then we're going to do a system-side design with SysML. And then after that, I'm going to stop, because after the design, there's back and forth with virtual modeling and with creating the prototypes. For all of these pieces, they were prototypes before the final thing was put together. Okay, so let's get started. I don't think anybody else is coming in. Okay, so it all started on Saturn. I bet you didn't know that Saturn had blood analyzers. It all started on Saturn in 1939. You see Dale Arden? You all know Flash Gordon? No? Well, there's Dale Arden. And this is a people mover on Saturn, and she got into this thing, and the people mover whisked her away. And this was in 1939, and there was the maglev, because this thing ran on a maglev track. So there we go, 1939. Now, what I'm going to do is I'm going to start with the Unified Requirements Modeling Language, which is, the URML is very simple. You take SysML and you change the symbols. And so that they can be a little more expressive. So, but they are the same symbols. The oval of SysML and UML, which means process. This is a process. It could be a high-level process. It could be a low-level process. And the square represents the entire system. Okay? So, well, I'm not going to do that. So here's an example of my URML, which was used to capture the requirements on this project, but not the architecture and the system. So you'll notice that, by the way, this is for free if anybody wants it. The only requirement is you have to have, what is it, the Sparks version of Enterprise Architect, the Sparks version of the modeling tool, and you just plug it in and run it. And what it does is it takes those terrible squares and circles and replaces them with things like an ambulance, which means aid, or a person, and there's a hazard. You can see the triangle represents a hazard. Person's getting their hand stuck. And so this is just about the diagrams that you see in the URML. And I want to show you this because the first 2 or 3 diagrams talking about the process, talking about the requirements, are in the URML. Okay, and then we switch over to the design, which is SysML. Believe it or not, this is all SysML. But it's just, you can figure out that like this would be an actor, you know? And well, I'll show you the SysML symbols in just a few minutes. So just to go over it again, we have the URML, which is the customer-facing analysis, because customers like pretty pictures, right? And they don't like to see a bunch of boxes. Customers do not like to see a bunch of boxes. Then we switch over to SysML, and we do the engineering analysis and the logical design. And then we switch over to mechanical engineering to do the physical design, and we create prototypes. Sometimes they're virtual. For some of the pieces of this thing, they were physical, like the people mover was physical. Okay, so again, requirements to high-level design was SysML. High-level design was SysML. The mechanical model was a 3D simulation. Pilot system integration and testing, and then manufacturing, including subcontracting. So a lot of the pieces of this thing was subcontracted. And I'll go into the chemistry in a bit. Okay, so this is what's called an outie and an innie. That's the outer block diagram. It's the block diagram in SysML. And here you see what's called an inner block diagram. Now, let me see if I can make this a little clearer. Well, those are just the IDs of the item. So here's the analyzer requirements. So we're in requirements here. So we have the sample analysis requirements. And here we have aspiration, dilution, sample analysis, quality check of the analysis, correlating the analysis results, and reporting the analysis results. That's easy to do, it's just boxes. And then underneath that, you can, any one of these you can explode to a diagram underneath. And here we have the 3 perform the sample analysis. We have clinical chemistry, immunoassay, and biochemistry, biomedical. Now this part was very interesting because these were all done at different facilities. And so the systems engineer, the chief systems engineer, had to make sure that when everybody was done, each of these pieces would plug into the analyzer and work. And I'll show you how that works in a minute or two. Here's an example showing the explosion. This is pure SysML, showing the explosion of pieces of the analyzer. And here we have what's called a vessel mover, because you can have 2 things. You can have the tester move, or you can have the test tube move. So the solution is obviously move the test tube, right? It's a lot easier to move than a whole analysis box. So we have a vessel mover, and then we have the architecture model, and here you see the other pieces, including performance requirements, packaging and shipping, manufacturing. See, the thing about SysML when you start, unlike UML where people start by doing a program, In UML, people start by doing a program. In SysML, people start by doing the entire environment. And then from the environment, they drop down. For example, this thing includes, I don't see it here, includes end-of-life disposal. How do you get rid of the thing when you're done at the end of life? A reason for that, one of the reasons for that is, I don't know if you're aware of it, but in Europe, there's a requirement that any electronics equipment has to have, before it can be brought to the market, has to have a plan for end of life. Now, if we had plans for end of life for our nuclear reactors, we would have been in good shape. So you can see how important that stuff is. So you need to look at it holistically. And holistically is, how do I get it through the door, right? Because remember now, we're mechanical too. We're not just, we're the entire project. So how do I get it through the door? How do I plug it in? How do I hook up the waste? How do I hook up water? How do I interact with people of all different kinds who want to use it? How do I interact with the hospital's lab system? And once I have all that, then I can start. So here we see some physical constraints. Now, these are just boxes in SysML, but I have changed them to diamonds because I think they're very important. And if you look at a sheet of paper and all you see are boxes, you can get wiped out very easily, you know? So these are just boxes, but I changed the symbol. And here are the physical constraints. We have ergonomics, common base, system footprint, number of modes it can have, system SPC, and the saleable, saleable configurations. In other words, how many configurations can I sell? Because we have to, when we are systems engineers, we have to look at the money too, you know? Whereas it's for programmers, it's full speed ahead and damn the cost, right? So we have to look at the money also. So if you look at it from the point of view of the test tube, the life of the test tube, this is pre-analytical phase, the analytical phase, and the post-analytical phase. And we're talking here about the sample management process because there's a lot of work that goes on before the measurements are taken, and then there's a lot of work that goes on after the measurements are taken. You know, per the FDA standards, although I don't know what's going to happen now. Here we go. So here are the key processes. Now you see the square box, that's a system. And this is what's called the context diagram. No, it's not, I'm sorry. And here you see all of the processes, oval means process, all of the processes surrounding that are associated with the analyzer system. And you'll notice that the eyeglasses down there mean that there's diagrams underneath this. You just double click and you get to a low level diagram. Okay, and it goes way down. Okay, because obviously different people are going to be getting different pieces of this to work on, but they will have to fit together. Now here's what's called the context diagram. This is the same in both UML and SysML. The context diagram is everything outside your system that has to connect with the system. And if you leave one of these out, as you do the engineering and drop down to lower levels, if you lose sight of it, someone's going to say, oh, what happened to the connection for the lab system? What happened to the connection for the local tech support? How does local tech support get into this thing? So you got the hospital IS, the lab environment, the printer, and all of these things that the system has to be able to support that are external to the system. and woe betide you if you forget one of these, right? And that's why it's important to look at it holistically when you start. You don't look at it holistically when you start, you're gonna wind up with a highway with no entrances or exits. Okay, so here's patient sample management. And here are all of the processes associated with sample management. Again, these are like, this is UML, but I'm using something a little bit more expressive because this was customer facing. Okay, I'll show you the system facing momentarily. And here we have centrifuge samples and decap samples. Decap samples means you have a test tube and the tube has a blood sample in it and you're going to run it into the analyzer. Now, in order to prevent evaporation or spilling, they like to cap the samples. Put a little, you'll see what they look like, a little red or white cap on them. And then the question is, does the technician have to uncap them, or can the machine do it? Now, when I was working on it initially, it was classified as a future, but there was a problem because the competitor had decapping. So now the device does have decapping. I don't know, you may see it in the video I'm going to show you, the decapping process. Okay, so here we load and identify the samples. We can, you'll notice that a future is RFID. I think they just went with a barcode. They decided not to bother with RFID. And so the barcode was plenty. And you can identify samples without a barcode by saying, hey, technician, you got a sample in your sample drawer with no ID on it. And then you get an ID. I'll show you how that works.
Do they assign priorities to these?
Oh,
Like
yes.
This one is most, and this one's least.
Yes, they have this thing called stack, which means immediately. You can assign priorities to all of the samples. But keep in mind that the analyzer is going to do about 4,000 samples an hour. Okay?
But even in this diagram, do you consciously assign priorities to these?
Well,
elements?
the technician puts the priority in as part of identifying the sample. Okay, they can identify the sample on they get a big screen with pictures of all of the samples and they can identify all of them, and then they can assign priorities. But they also, as you might be aware, let's say you're in a hospital and someone's doing an operation and it's critical, and they go running upstairs with the sample and they say, I need this right away. And that's called stack. And they stick it in the machine and zip, 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 they get the results, prints out on a piece of paper, and down they go back to the operating room. Okay, so here is the architecture. And this is pure SysML. Okay, so here's the medical analyzer system, and we have the what do you call it? We've tagged it as a system, and then we have sample source and sync during assembly. We have refrigerated sample storage. We have the analyzer mode. We have immunoassay, chemistry, and they've added biochemistry, I believe. And then they have to have a reagent storage area and feed. Now, decapping, I think I mentioned decapping is in there, and you'll see it. They also initially did not have biochemistry. For example, AIDS, COVID, things like that. And they added a third module now when they do those. Because I worked on this in 2013 and it's 10 years later. So I think the thing went to market around 2016, 17. Okay. Here's the vessel mover down here. And here's a comment that you can put on. And here's the lab assistant, because the lab assistant is in the loop. You can't, the lab assistant has to take the samples and put them in the sample drawer, right? So you need it, and that's a person. I suppose you could get a robot to do it at some point in time, but that hasn't happened yet. But there is a robotic arm that takes the sample, and I'll show you how it works with that. Here's the sample bar scanner. The robotic arm is to and from the vessel mover, which I will show you in a bit. Okay, now this is called a block diagram. This is a block diagram of the vessel mover, and here it has partitions, and here you can see parts of the vessel mover. Here's coil boards, because it's going to move the samples magnetically. And here you see components of it, and here you see references, and here you see properties. You're going to hear the word puck. The puck is basically the little car that the samples move in. So you saw Dale Arden in that big puck, and you're going to see little pucks, and you'll actually see a movie of the little pucks in a bit, okay? So we have, that's the other thing. This is very clever. So the question was how to add the reagents. Like you're looking at it, and you know, with the printer, you get a thing that pops up and says red low or cyan low, and you have to replace it. Well, what you do here is you load it like a sample, put it in, and the vessel mover moves it around, takes out the old one, sticks in the new one, and it's good to go. So nobody has to touch it once you've loaded it on the railroad car. That's it. It's amazing, isn't it?
Yeah,
Yeah.
I always screw up when I open up my printer.
I'll show you a picture of them doing that. Okay. Here are the various, this is a state diagram. Now, usually you see state diagrams as ovals, right? For those of you who's worked with state diagrams, they're ovals, but here they're, what do you call them? Rectangles with rounded corners, you know? They're rectangular in nature. So you have analyze a startup. Once it's started up, the machine goes to idle, the drawer opens, and then nothing's going to happen until the operator closes the drawer. And then you have to wait for a puck to show up. Once the puck shows up, you pick from the drawer with the robotic arm, you put it on the puck, which is really like a railroad car, and then off she goes. And here's the puck sample, and here's a request information. So when it gets to the station and you get information, what are you? I'm going to analyze you. I'm not going to analyze immunoassay in chemistry section, obviously. And here we have something else. We have the ability to store the blood in a refrigerated area. So the analyzer actually has a storage facility for racks of samples that they were to put on hold for recall later. No person touching them. Here's a picture of the puck. There's the magnetic track. You can see it's a silver looking thing. And here's the puck. It has two tube positions, one here and one here. They normally just run one sample per puck. The reason for that is the second one's like a passenger. They have to go to the same location. And it's nicer if you can just move to different locations. But sometimes when they want to go to max number of samples, they'll go around with sample A, and then they'll go around again with sample B, both on the same puck. Okay, so here's what the sample drawer looks like. And here you can see, here you can see capped, and here you can see decapped. Now the capped, in some cases, you can stick a needle through this little hole there. And here's something ready to go in. And then what happens is once this thing's filled up, they just close the drawer and off she goes. But you don't touch anything once it's inside. And the cold storage, the robotic arm can pick up a sample and move it into cold storage if it wants. And then it's in racks just like these, but in the cold storage area. And the system keeps track of where every sample is at any point in time. That's, for a programmer, that's easy to do, right? But if you have volatile memory and the power goes out, watch out. That's why you want to have non-volatile memory for this. Okay, here's the sample mover I was telling you about. There it is. Notice here they only have one sample on each puck. And this one's decapped, and this one still has the cap on. And here's the track. So here's a station where analysis can be done. And what will happen is you'll notice that it's just not straight, that this can switch and go in here. There's one already in the analysis station. You can see it in there. So it's pretty nice because they have different loops. And then the other thing is once it goes around, let's say you do one sample, which is one set of analyses immunoassay, and then they want to do biochemistry, well, just bring it around again and do the next loop. Yes.
Are the tubes moving right to left or left to right?
The tubes are moving left to right in the front and right to left in the back. It's like a train loop. It's an oval. Let me show you what it looks like. I don't know if there's anything I can draw with here.
I get it.
Gotta be erasable.
I know.
I once drew on a board and it wasn't erasable. Where did I think out for that?
It's a directional marker.
You're right. How about I go over to there?
Yeah, put it on here. Okay.
Okay.
I'll hold it.
Here's loading and unloading. Here's what the track looks like. Analysis station, analysis station, analysis station. That's it. Thank you. Do you see that? Now, the nice thing about that is I can plug in more modules. I can take another assembly and add it on, and then I can add another one after that, and another one after that. After all, it's a train. So, thank you.
Okay.
And they will plug in, and I'll show you what a big one and a little one look like. So, Dennis, we were talking about the reagent.
Yeah.
Here's the reagent being added. Now the reagent uses a different track because it's bigger than a sample, but same principle, it rides on a track and goes around, and then it gets loaded in the analysis station. You can see it here being put in, how easy it is. It's just open the door, drop it in, close the door. Now, why is this important? This is important because this is how the company makes its money. The company doesn't make its money on the analyzer, which initially is very expensive, but that's not going to cover all the costs and the engineering. So you pay for the reagent, just like you pay for for the ink. in a printer, right? Just like you pay for the ink. It's the same idea. So you pay for the reagent, and the reagent comes ready to put in. You just take the cover off, and in she goes. So the thing is, would a programmer think of that? Would a programmer think of that? And that's why you need systems engineers, because programmers have tunnel vision. Even software engineers have tunnel vision. You need to look at the whole system holistically. And then you have to say, how am I going to make my money? And then you have to interact with the salespeople, the mechanical engineering people. You have to interact with the chemistry people. I had to go to 3 different locations to talk about how we were going to connect the station to the analyzer, because each location I went to was doing a different type of analysis. And we had to coordinate with all 3. Okay, so here are the sample states, which I can't see from here. We'll come over here. I still can't see it, so I'll put my glasses on. So the samples are loaded into the tray. It's placed in the analyzer drawer. The samples are moved to the analysis position, wherever that is. The samples are analyzed. The results of the analysis goes to the information system, the onboard information system, and the samples are moved to the sample drawer, or they're moved to refrigeration. And then the samples are unloaded from the samples drawer, and in parallel with that, the analysis results are reported. So here we go. Everybody recognize this? This is a sequence diagram. This is in both SysML and UML. It's a sequence diagram. So what happens is, vertically, here, you have the equipment or the people, what's doing the work, and so you can see who's doing what. So here you can see that the medical tech is putting the sample rack in the drawer, and the medical tech is removing the sample rack from the drawer. And here we have a loop for doing the analysis, because it makes more than one sample. And so you do, while there are any samples remaining, this is a loop inside SysML that allows you to go round and around. You get the sample tube, tell the robotic arm you have the sample tube. It places the sample tube on the vessel mover. It moves the sample to the analyzer. The analyzer identifies the sample and the sample type, sample ID. Then it analyzes the system and it reports the results using the ID. And then you store the information management system. You store the analysis results, and then the sample, in the meantime, in parallel with that, the sample goes back to the vessel mover, and the sample goes back to the robotic arm, and the sample goes back to the rack, and then you can remove the sample from the sample drawer. So,
Brian,
yes,
as a software guy, I love these pictures.
you do. This is SysML, no change.
I understand.
Yeah,
And if I'm implementing, let's say, the vessel move,
right.
then I know anytime an arrow comes in,
Yes,
that has to be a function, an API, an event, or something like that, that my particular part of the system has to be able to handle. And
that's
if I
correct.
don't handle it, then I've screwed up the requirements.
Right, okay. So just by way of comment, I am not going to show you the software. You know, these messy copyrights, I'm not going to show you. And by the way, this thing is patented. So everything, if you go and you look at the patent office, you'll see all the patents come pouring out to this guy. Okay. And here's the sample drawer details. So you can see what's happening just in the sample drawer. These things are intelligent, right? So and one question is, would you keep the sample drawer? Would you give it some intelligence to do this work? Would you keep everything in one place and then just have an event, kick it off in parallel in one location? So it's probably better to decentralize. Because then you can have one piece go out and the other piece is still working. As opposed to having everything in one location, one long software program, and that goes out and the whole thing goes dead, you know? So that's how this is done. It's compartmentalized. And again, here you have the sample drawer. And here you have the sample drawer includes the robotic arm and the gantry that puts the sample from the drawer into the puck. And then you might have you have a PPS position that's a primary point position, and then you have the non-primary. And here you have request to information from the SIM. So this is true object oriented because everything is an object. And the tube is an object and says, here's my ID, right? And every little piece, the robotic arm has intelligence, the vessel mover has intelligence, the analysis stations have intelligence, they all have intelligence, and they all work together. So one of the analysis stations can go out, and the others will just keep on cranking. Okay. And sometimes if it's a very high volume day, and you want to do 4,000 samples, you might have more than one analysis station doing the same thing. Okay, so you can do it in parallel. Okay, here's the sample mover operation. Want to see if there's anything. Here's the sample planner, here's the vessel mover, and here's the analyzer. And so these are the three pieces. And here you have the sample mover in the state. This is a state diagram showing the sample mover. This one wasn't interesting. Okay. What?
I've been to church and
That's true. I'm not very,
Eyesight.
I hope I didn't break the camera. I'm not very photogenic. Okay, so here's the system operation. Okay, we talked about mechanically the structure, but everything it does, and here's the basic operation, and you can see the operation of the system includes the system environment, the utilities, right? You don't want to forget about plugging something in from the wall, the managing errors, system state management, if there's a problem, manage the temperature, because the temperature that these things get analyzed in is very sensitive. It has to be at a certain temperature. Temperature can't go higher than a certain amount. And power management. What happens if the power to the building goes out? What happens if all of a sudden you lose power? You know, things like that. And so the utilities are very important too, because you have to plug it into the wall. You have to do hookups, you know, of water. What are you going to do about waste? You have to have facilities for removing the waste. So these are all things that a systems engineer would consider, as opposed to a programmer or a software engineer who might think about the software side of these, but wouldn't think about the mechanical side or the electrical side. So, and here's quality assurance. So you have quality control. Obviously, for analyzing a sample, you don't want to tell a woman she's pregnant when she isn't. You know, that's not very nice. Or telling a person they have cancer when they don't, or telling them they don't have cancer when they do. So quality assurance is very important, and that breaks down into a whole bunch of different requirements, mechanical requirements. Okay, so Yeah, so I'm approaching the end of the talk. And I just want to tell you that for those of you who are just getting started in SysML, when I taught at Georgia Tech, I created a set of cheat sheets. And here's my email. If you'd like it, just email me and I'll send you the complete set. There's one cheat sheet for each type of diagram. And the question then is also the issue of profitability. You don't want to make something if it's not going to be profitable. So as usual, Siemens that makes this product, they have a problem. The problem is their old analyzers is still running. And it's like anybody who buys a printer, you know, you buy a printer and you start using it, and they come out with a new version of the printer, but you don't want to get rid of yours because it's still working, right? So that's a problem they have, is getting rid of the old printers. Or in this case, getting rid of the old analyzers. Because the newer analyzers are more profitable. Okay. So, but it's still profitable, not as much as they'd like, because the old facilities are still out there. The old analyzers are still out there making money. And remember I talked about modularity, how like a model train, you can plug sections together. And here we see some of the sections, and you can see that you can run around on these things like the railroad train goes choo-choo all around the tracks. And every time you see a black top, there's a track underneath it. And it can be directed from the brain, can tell any one sample, you know, where to switch, kind of like a rail yard. Switch and go off in this direction. Here's a junior. They realized they had to make a smaller one because in addition to hospitals, you have small clinics, you know, and they wanted to be able to provide smaller size objects, smaller size analyzers that did the same thing. Here's a smaller one. So you can go upscale and you can go downscale, which is very, very nice, you know. So you can go upscale and you can go downscale. So you can start with this and then move into this at a later date. That's basically how the product line works. So it's immunoassay and chemistry. So in summary, the systems engineering approach led to a modular design, comprehensive top-down requirements, including environmental factors, including the outside. Prototype testing in parallel with analysis and design. They had prototypes of the track up while they were designing it to see what would work. One of the problems they ran into with the track is if they ran it too fast, you know how you have a glass of water and you're walking and all of a sudden you stop and it sloshes, right? So that was a problem because these things move very fast and they like that. So they had to cap them. They had no choice but to cap them because if they didn't, they'd have sample all over the place. Now the other thing that was interesting is when I was working on it, I saw a requirement that it had to be so many feet wide. It couldn't be wider than this. So I asked, why does it have to be 4 feet? Why can't it be 3.5 feet? Oh, because it has to fit through the door of the hospital. When you're installing it, it has to get through the door. So it would have been nicer if they said, you know, it has to get through the door of the hospital, where you're going to put the analysis machines. And I would have just then sent off a letter to all the hospitals where it was going and saying, how wide are your doors? So I didn't miss anybody. Anyway. So I said again, the only holdup to full profitability is the older products are still in use. So they can't get the full benefits of it. Okay, so it all started with Buck Rogers. So I'd like to show you a movie, and then you can ask some questions after I show you the movie. Dennis, I might need your help here.
Okay. Just,
Hmm?
Oops, sorry. We're just going to slideshow. Close this.
And it's going.
All right. Good.
Just taking question.
And your sound?
You can leave it on. There's not much there.
Okay. Hit the space bar to play.
Okay, so you can do it in as little as 6 square meters. You can have integrated automation. You can see there are the samples being moved along. And here sorting and archiving samples. And there again, you can see the sample mover. And someone had asked about priorities. So you can always jump the highest priority sample to the front. Because of the structure, it's very easy to take the highest priority sample and just send it on out. So it connects to the laboratory system very easily. And of course, because it's on the internet, on Ethernet, managers can watch it in their office. You don't have to be. I don't think though that you can run it from home because you have to load the samples and then take the samples out when you're done. Okay, so that basically concludes the talk. The thing is, I started working on it around 2012. It was operational about 2017. And they had a lot of trouble selling them initially for the obvious reason that there were so many out there, so many of their older machines out there already, but they've gradually been replacing the older machines, especially at the bigger hospitals where they're very desirable because of the number of samples per hour that they can handle and the number of tests they can do. Imagine if you have different tests, you can just unplug one test and plug in a different one through the reagent by putting different reagent on location. You have to clean it first. You throw a little water in one of the sample jars and move it around and run water through it, and that cleans it out. And then you can run other samples through it. Okay, so systems engineering includes business, it includes environmental issues, it includes people issues, it includes all kinds of external issues like power, um, water, all the different utilities, lighting. It includes all, even includes the size of the room so you can get the machine in. The weight is very important. And whether you have to take it apart to get it into a building, it has to be built in such a way that you can disassemble the pieces, slide them in, and then connect them once they're in. And all of this is systems engineering with electrical engineering and mechanical engineering and civil engineering and bioengineering. All of those put together. And that's what a systems engineer does. It's the integrator for all of those different all those different things. And the people under you, as a systems engineer, they all have specialties in these different areas. And then you start teaching them systems engineering and they start moving up. So the other thing I would say is anyone who's a systems engineer has typically started with a specialty. I mean, you don't walk in the door and say, here I am, I'm a systems engineer. You go in and you do OJT in your specialty, which could be electrical, civil, mechanical. And then once you've done a couple of projects, you get bumped up to assistant lead, then you get bumped up again after you've done a lot of them. The thing is, a lot of people go out and do fly fishing after they've done one or two of these because it's very stressful. And you're dealing with people in many locations with many different skills, speaking many different technical languages, and you may or may not get along with all of them, but the idea is to get along with all of them. And to gently suggest that they do it a certain way, as opposed to saying, you do it this way. You have to suggest they do it a certain way. Okay, I
Can we
think.
take some questions, Brian?
Absolutely. Thanks for reminding me. Yes.
I'm interested in, like, you talked about all these different like physical models, like chemical models, bio models. How do they, I mean, technically, it's a SysML modeling language. How does that dovetail with the physics models that run the track, things like that?
Well,
Will you please repeat the questions because it really doesn't reach you.
you have so you have all these different analysis models. Is that what you're saying?
Yeah, like, I can go up and talk there. That's what
Yeah.
Okay.
Yes, my question is, well, what it says SysML, it's a modeling language, right?
Yes.
But there's the model for the track, right?
Yes.
The physics model.
Right.
And there's a whole bunch of other, like you
Right.
described, a whole bunch of other models.
Right.
Do they integrate with the SysML in some way, or is it just separate?
Only electronically through a link. So if you're going to do mechanical engineering, I showed you a mechanical engineering drawing. You do the SysML down to a certain point, and then you click, and it brings you over to mechanical engineering, which could be in a different type of analysis too. I've also worked with, what is the architecture? What's the big architecture tool called? Not Adobe. What's that?
AutoCAD.
AutoCAD. I worked a lot with AutoCAD, and AutoCAD integrates very nicely with this. Yeah, so you can drop down a level, and then you get all your wiring, your mechanical specs, and so on. And you can go over to mechanical diagrams, and you can even go over and look at the virtual models that are there in the system, because they do virtual models typically, and then after the virtual models, then they'll build a physical model. They'll try to do a it's very expensive to do a prototype. Very expensive, much cheaper to do it virtually. So you do it virtually, and then once it's confirmed you got what you want, then you build a physical model, and then you go through it all over again if there's an issue.
All right,
Okay?
I think we're at time.
I have a question.
One more question.
I'll go up here so you can hear.
Mhm.
My question is, how do the design team use SysML? Are they all users and they get a read-only view so that they can go in and critique it to identify errors or missing processes?
SysML is a tool for design engineers like any other.
So all of them have access to it?
All of them have access to it. All of them learn it. Now, the thing is, that's a good point, though, because you do take snapshots and you do backups of a particular model in time. And then, so if you do the next model, if someone makes a mistake, you can always back up to the previous one.
Good question, man.
So it's a little bit like software. You put it in a repository and you back up. Okay?
If I may ask a question?
Yes, you can ask
it's
a
very
question.
quick.
This is online.
Okay, I have two, but one is instantaneous. Who is Brian Berenbach or something, the one that has the copyright at the end of the slides?
That's me.
That's you. Okay.
Yeah.
Thank
Brian
you.
Berenbach.
And
Yeah.
and the important question is, first of all, this is an impressive presentation. I like it. It's a very complex system which implies a lot of art and very well documented. I think. I wonder, did you build this directly to the end like production platform, etc., or did you implement a simulator or something to prove properties and things?
I was involved in the creation of the design, and we were doing prototyping and virtual modeling while we were doing this. There were many reasons. For example, something very simple was, will the robotic arm fit in the container, you know? And the only way to do that is with a virtual model. It's the only way you can see that that the thing's going to work approximately, and then the only way to verify it is with a physical model. You have
And
to
you
build a
tested-
prototype.
You probably tested components separately before putting the pieces together.
The components are very often subcontracted.
Thank you.
Okay,
Great work.
Okay, all right.
Great work. Great work. Thank you.
Okay, so you had my, if anybody wants the cheat sheets, you had my email at berenbach@rowan.edu. Okay, I'm done. Thank you very much, everybody.